Hello and welcome to this presentation of the CIRPe2020 Global Web Conference. The title of the presentation is Towards Design for Interoperability in the Context of Systems Engineering. My name is Sjarov and I'm a research assistant at the Institute for Factory Automation and Production Systems of the Friedrich Alexander University Erlangen-Nuremberg in Bavaria, Germany. The agenda of the presentation is as follows. First, I want to motivate for the topic of interoperability. Then I will briefly lay out the state-of-the-art in Design for X, systems engineering and interoperability. After this, I want to introduce the Design for Interoperability by providing a definition, the corresponding levels, as well as a method to implement it. I will finish with a conclusion and an outlook. The manufacturing industry is currently driven by the paradigm of Industry 4.0, which itself implies an ever-increasing degree of digitalization. This is enabled, among others, by advances in information and communication technologies, ICT. Within Industry 4.0, the integration of technical assets such as cyber-physical systems is of a major concern. The integration, on the one hand, is realized with and between IT systems horizontally, which means assets of the same type, and vertically, which means within the hierarchy of the automation pyramid. On the other hand, an integration of information along the product lifecycle is envisioned. As the integration of assets implies exchange of information, interoperability comes into play. In order to plan for this required interoperability within the systems engineering, the design for interoperability is going to be introduced in the following. This slide covers the fundamentals of Design for X. The roots of Design for X can be traced back to at least the 1950s. Over time, the collective term Design for X emerged to cover the rising number of proposed design principles. Design for X is often defined as making decisions in product development related to products, processes and plants. There, Design for X comprises guidelines and criteria for target properties as well as methodologies for their implementation. Within several reviews of DFX principles, authors identify different ways to structure them. At first, the general scope can be distinguished. It reaches from product over system to ecosystem. Then, the product DFX character can be a virtue of a product, such as being very ergonomic or user-friendly, or can concern the product lifecycle, such as design for remanufacturing. The focus of DFX is either internal, concerning the production, or external, concerning stakeholders outside the organization. Finally, the application of DFX principles can be characterized according to the corresponding development phase, being requirements definition, concept definition, high-level design or detailed design. After introducing Design for X in general, the systems engineering is a second pillar of the Design for Interoperability. Systems engineering is by the IEEE defined as an interdisciplinary approach governing the total technical and managerial effort required to transform a set of stakeholder needs into a solution. Nowadays, being driven by a multitude of different models, it is often referred to as model-based systems engineering or MBSE. Within systems engineering, different domains are to be integrated: the mechanical, electric and software domain. With the ever-increasing computation power and other means of information and communication technology, the development focus and value added has been shifting towards the software domain for many years. As the information interchange between different systems becomes increasingly important, the engineering of a systems interface becomes more important as well, finally leading to the questions of interoperability. Now, for the state-of-the-art of interoperability in general, we first take a look at a common definition. Interoperability is the ability of two or more systems or components to exchange information and to use the information that has been exchanged. Several reviews on interoperability lead to the following conclusions. Many current challenges in the context of smart manufacturing lead to the question of interoperability. Then, many different models of interoperability were designed. Nonetheless, many of them share a rather weak impact due to their high inherent complexity. Among the most cited models are the Levels of Information Systems Interoperability, LISI, the Organizational Interoperability Maturity Model, OIM, and the Levels of Conceptual Interoperability Model, LCIM. Different domains of interoperability were identified by different authors, where the most important are the technical, operational, organizational, as well as systems, data, information, and process. For the subsequent presentation and the design for interoperability, only the boldly marked domains are relevant, which are technical, systems, data, and information. Now I want to introduce the design for interoperability by first providing a definition. The design for interoperability comprises knowledge, guidelines, and principles for designing digitally interoperable systems, which means systems with the ability to digitally exchange information and interpret its meaning within a given context. In order to characterize design for interoperability in the context of existing DFX principles, the previously mentioned categories can be used. The scope of design for interoperability is overarching. It covers components as well as systems and systems of systems. Concerning the character, it is foremost a virtue of the system itself. Nonetheless, for example, via means of software updates throughout the product's life cycle, also this perspective is of interest and needs to be considered. The organizational focus varies depending on the specific scenario. Both an internal as well as an external focus can apply. This is further blurred as digital communication occurs everywhere, both within organizations and systems as well as between them. Finally, regarding the classification according to the development phase, design for interoperability reaches from the requirements definition to the detailed design, there spanning the whole design process. This slide presents the levels of interoperability. They are a synthesis of the LISI as well as the LCIM. Furthermore, they are enriched with 2 dimensions of the reference architecture model for Industry 4.0. The 7 levels of interoperability are taken from the revised and refined LCIM. They are of a hierarchical nature, where each level implies all capabilities of the lower ones. Level 0 stands for a standalone system not being interoperable with its environment. In Level 1, systems are technically able to exchange digital information, which means raw bits and bytes. When a common data format comes into play, Level 2 is reached. The systems use a common alphabet, though the actual meaning of the information remains unspecified. This is the requirement for Level 3, the semantic interoperability, where the meaning of the data needs to be specified explicitly. In Level 4, the context of a system state needs to be incorporated into the information interchange. This will provide meaning to the exchange information, thus means of defining possible states and exchanging are to be incorporated. Here the use of ontology comes into play. When the possible states, aspects and capabilities of a system change over time, dynamic interoperability is needed to ensure proper information exchange at Level 5. In the conceptual interoperability Level 6, furthermore, all modeled assumptions and constraints of the systems need to be explicitly available and understood by the partnering systems. The levels of interoperability are enriched with 3 aspects: inspired by the LISI. The standards aspect comprises definitions of data formats, information models, process models, state models, standardized ontologies, and so on. The applications describe the intended use cases that require the associated level of interoperability. The infrastructure and data aspect of interoperability comprises on the lower level networking protocols and technology, and on the higher levels service architectures, database schemas, and their explicit formalizations, for example via ontologies. In addition to existing models of interoperability, dimensions of the reference architecture model for Industry 4.0 are taken into account. The hierarchy dimension ranges from a single device over stations to entire production systems. By locating the system within the hierarchy of other Industry 4.0 systems, requirements for interoperability can be identified specifically. Finally, the life cycle dimension is of particular importance. There, the designers need to define the intended use of the system as well as its associated digital models throughout the system's lifecycle. In this slide, a general method for implementing design for interoperability is presented. To structure the activities comprising design for interoperability, the systematization into data engineering, process engineering, and constraint engineering is used. Then a general 5-step method provides further guidance. At first, interoperability is viewed as a fundamental aspect of a system. Requirements are to be defined accordingly. There, two views are to be considered. The internal view concerns the requirements needed between the system's components, whereas the boundary view analyzes the relation of the systems to its adjacent systems and environment. In step 2, a concept of the required technology stack is to be developed. This comprises the identification of needed levels of interoperability in order to satisfy the requirements. Fundamental decisions, for example, if to use ontologies, take place here. In the third step, the high-level design of the corresponding technology stack is realized. Standards, data formats, and ontology types are to be determined. Furthermore, architectural decisions concerning hardware, software, and services are to be made. Then, in the fourth step, the detailed design takes place. As every model-based systems engineering approach incorporates a test phase, this also applies to the validation of requirements for the interoperability. An underlying paradigm for the whole design for interoperability is the planning for maintainability and updatability of the entire technology stack. This is especially important as the development of the involved information and communication technology takes place in a continuous manner. Concluding the presentation, the design for interoperability unites the domains of systems engineering, design for X, and interoperability. In the paper, we introduced a unified model with levels of interoperability as well as a method for implementing it. In the future, the model and method need to be revised according to the current state of technology. Also, derived principles as design for digital twin need to be investigated. And now I want to thank you for attending this presentation. Thanks and goodbye.